Okay, we are now ready for the grand finale of backpropagation. We're going to look at backpropagation for training multilayer perceptrons with an arbitrary number of neurons in each level. Now, just to recap what we've done so far, we actually did have a solution for this, which I called the lazy calc solution. What we did in this solution was we perturbed each weight and each bias at every layer just a little bit, and we saw how the loss function changed. And that was how we estimated the influence of each parameter on the loss function. So really what we were doing was approximating the derivative. Aside from being just an approximation, though, there is actually another downside to this, which is every time we twiddle just a single parameter, we have to reevaluate the entire network from scratch. So when we get the loss function, we're evaluating the entire network, which is doing this series of matrix multiplications. So the time complexity of this is the time it takes to evaluate the network times the number of parameters, which is really bad because we're going to have a lot of parameters when we scale this up. For example, if we have 100 neurons feeding into another 100 neurons, that's going to be 10,000 parameters. So 10,000 times the cost to evaluate the entire network. And evaluating the network is not cheap. So what we saw is, okay, we're going to, number one, try to be a little more correct with the derivatives here, rather than using a secant approximation. And we're also going to do a dynamic programming algorithm. So we're trying to estimate the influence of each parameter on the loss, so each weight and each bias. What we can do is actually start to derive what the derivative is analytically for this algorithm called backpropagation, and realize that if we start from the outside in, we can make use of things that we've computed before. And in the end, this is just going to take one forward path and one backward path to compute all of the derivatives of the loss function with respect to every parameter. So rather than taking the number of parameters times the evaluation function, this is only going to take 2 times the evaluation function, a forward path and a backward path. And so that, even for 100 to 100, which is not really that much for a single layer of an MLP, just that single layer would have 10,000 parameters. So 2 is significantly faster than 10,000. So just to help justify why we're going through the pain of doing this. So this is an example, again, of a dynamic programming algorithm, just like the Viterbi algorithm and dynamic time warping. And for those who have had data structures, it's just like the edit distance and things like that. Seam carving. Okay, so a dynamic programming algorithm because we're going to remember things from the forward path. And then on the way back, we're going to remember our subproblems, which are the derivatives with respect to the outer layers first. And those will allow us to march backwards towards the inner layer, eventually all the way back to the input. All right, so I'm going to try to move towards a more general formulation of this dynamic programming problem. To do that, let me try to generalize what I had written here for this 3-layer single neuron case. So I've already written this ahead of time because it took me a little while to decide what notation I wanted to use. But so if I just pull out part of what I was just looking at, so there's a lot of symmetry here and we start to notice some patterns. Let me just say I'm in the middle of a big old one of these things and I want to understand the influence of this process on just one of my neurons in the middle. So what I can do is realize, okay, here's the dependence that I have. Turns out if I can remember what the derivative of the loss function was with respect to a k plus 1, which is just the linear part, so the weight times hk plus the bias. If I can remember the derivative of that, then I can use that, and then I can multiply that by the derivative of the nonlinear function, and that will give me, and also multiply it by weight k plus 1. And that'll give me the derivative of the loss function with respect to the bias at this neuron. So if I remember this from the last time, I can compute the derivative with respect to the bias, which actually is the same thing as the derivative with respect to AK. Okay? So that's something I'll remember for the next time. So if I remember the derivative with respect to AK plus 1, I can compute the derivative with respect to AK, which is the same as the derivative with respect to the bias. And I can remember that for the next time. And so then if I want the derivative with respect to the weight, I just have to tack one more thing on the end of it, which is HK minus 1, the input into this neuron from the layer before it. Okay, so I remember the AK plus 1 from the layer after it as I'm coming back in the backpropagation, and I've already computed this from the forward pass. So with those two pieces of information, the derivative with respect to this and just this straight up, I can compute the derivatives with respect to the weight and the bias at this level. So these are now the learnable parameters that I'm learning how to tweak. All right, so I'm learning their influence on the loss function. All right, so this is now the general formulation here. And let's just take a little breather, because now I'm about to. So this is the general formulation just for a single neuron the whole way through, but I'm about to ramp this up and talk about arbitrary number of neurons in each layer for multilayer perceptron. Okay, I want to remind ourselves of the general formulation of a multilayer perceptron. So as opposed to this one-dimensional case that I had, for a general multilayer perceptron, I can have as many neurons as I want in each layer. And so if I'm considering the effect of these weights here, what I have, I'm in the middle here, I have the outputs from this layer. There are 4 of them, I'm calling them X here. And then I have this other layer, which is going to have 5 outputs. And I take the output of everything in this blue layer and feed it as an input to everything on the next orange layer here. So every output here gets fed as an input to every neuron on the next layer. And so in this example, I have 4 outputs, 4 neurons in this layer, being fed into 5 neurons in this layer. And so that's going to take 4 times 5, or 20 different weights to describe. I also have a bias for every neuron in this next layer here. So I have 5 biases in this example. Now in general, we can summarize all this information with a very elegant matrix framework. So showing you here, what I can do is arrange the weights in a matrix where I have as many columns as there are inputs. And so that here is the neurons coming out of the blue layer. So I'll say here that maybe this is the number of inputs to this weight, to these weights, and then I'm going to have as many rows as there are outputs. So as many columns as there are inputs, as many rows as there are outputs for the weight matrix. And the bias, all the biases can also be stored in a matrix. Now in this case, I only need 1 column, because I only have 1 bias for every neuron in the output, as opposed to 4 weights for every neuron in the output. So I can store them as a column matrix. And if I do that, and I also store the input, so all the blue neurons, if I store all of those in a column matrix, then I can write the action of this entire thing as this W matrix times X plus B. So this entire operation here between these 2 layers can be written as the entire weights matrix times the input here to this layer plus the bias at that layer. And then we're actually going to apply an element-wise nonlinearity. So this could be like the logistic function or the leaky ReLU or something else, tan H. There's a bunch of options. So this is going to be our nonlinear function, which is going to be applied element-wise. So once we do the matrix multiplication and add the bias, we're going to have a number of outputs by 1 column. And then we're going to apply the nonlinear function to each element of that individually, and then feed that to the next layer. That will now become the input to the next layer, which will have its own weight matrix and its own bias thing here. And we can keep going. So that's how we do the forward pass. Okay, so I drew the more general case here. I'm going to focus on the action of this thing, which requires me to have some stuff from the forward pass right before it and some stuff from the backward pass right after it. And now I want to remind myself actually that instead of just having a single weight and a single bias, I have an entire matrix of weights. And so actually let me just decide how many neurons I have in each layer. So I'll say that I have, let's say that I have n neurons in this layer. In the layer that I care about, I'll say I have m, as in Mary, neurons in the layer after that. And I'll say p, I have p neurons in the layer before that. And so actually now, this hk minus 1, the stuff coming out of the last layer, is actually a column vector with p elements. This wk is actually a matrix. It has as many columns as there are inputs, so that would be p columns, by as many rows as there are outputs. So this would be a tall matrix here because it has fewer inputs than outputs just in this particular picture. But again, remember that these are arbitrary. So I've just done this for illustration. But so this is going to be a n by p matrix. And then this here is going to be a p by 1 matrix. So the HKs are going to be p by 1, or sorry, the HK minus 1, so the stuff coming into this. And we've got this weights matrix sitting in between. And then we have these biases, which we have one of those for every output at this layer here. So that's going to be an n by 1 matrix. And for the same reason, this HK is also going to be n by 1. And then finally, we have this AK plus 1, which we've remembered from the last time. So I say we've memoized it. This is the dynamic programming term for memorize. Maybe we should have just said memorize, but I guess when we say memoize, it reminds us that somehow we're in the middle of a dynamic programming algorithm. Okay. So we memoized this on the backward pass from the last time, so the layer right after this on the way back. And so that is going to actually have, so this AK plus 1, which you get with this matrix multiplication, is actually going to have m by 1 elements. And yeah, so that came out of a weight matrix in between here. Oh, I didn't want to cube there. It came out of a weight matrix in between here, which has as many. So this is WK plus 1 here. Let me get my nice little K plus 1 subscript here. So this is WK plus 1. That matrix has as many rows as there are inputs. So that would be, or sorry, as many columns as there are inputs, as many rows as there are outputs here. So that would be m by n. So it probably looks something like this in this particular example. All right. And yeah, I don't think I'll need this, but I might as well also just draw the biases here. So the biases in B in this layer coming out here, this is BK plus 1. So just making sure we understand all the dimensions of these things. That would be a column matrix with m by 1 elements. All right. But the important thing here getting started is that we've remembered this AK plus 1 from before. And actually, AK plus 1 is an m by 1 vector. And so that means that also the derivative of L, the derivative of the loss function with respect to AK plus 1, we're going to need to remember m derivatives. So we'll also arrange the derivatives along an m by 1 column vector. So let me go ahead and index this real quick just to remind myself. I'm going to give it an index. That is now a vector, which I'm representing as a column matrix. But this is a vector of all the components of AK plus 1. There are as many of them as there are neurons in this next layer here. And I'll index them with I. Okay, so let me go down here and I'll start to rework. I'll start to modify this equation a little bit to take into consideration the fact that we now have some vectors. So let me first just add that index that I have here. All right, so that's index I. Okay, so looking what I'm actually trying to compute on the left of the equal sign here, I want the derivative of L with respect to AK. So given that I've memorized the derivative with respect to AK plus 1, I want to work backwards and try to get the derivative with respect to AK. So just, yeah, the equation for AK is very similar. And I have the derivative expanded here. So let me try to visualize what that looks like in this case, because there's more neurons involved. So let's say that I was looking at, I'll just mark out here an I. Let's say I was looking at the ith component of the derivative with respect to AK plus 1. And let's say that I wanted to fill in the jth component of the derivative with respect to AK. So that's what I'm trying to fill in now. So I'll pick out a j over here. All right, so that j is going to influence I on a forward pass. And it's going to do so by the weight wij. Okay? And I should say that is let me specify, that is the kth plus 1 w, row I, column j. So let me actually be sure to get the right subscript here. So that's, and I'll make it a capital W now because we're actually taking this out of the matrix. So I'm using capital W for a matrix. So that's the weight here. It's capital W k plus 1, row I for the output to neuron I, column j for the input from neuron j. And so actually I guess I can go ahead and index that here as well too. So let me just move this over. And I'll say that, okay, cool, I am using this weight here. It's going to be a row I, column j. But actually, one thing I notice here is that the left-hand side just has a j. But suddenly this is a function of both I and j. And that's because this neuron actually influences every neuron that follows. Because again, this is a fully connected network that we call it a multilayer perceptron, but it's a fully connected situation here. And so this is actually fanning out and influencing every I over here. So what we're going to do actually is sum up. So I'm not worrying about this part yet, but I'll get to that in a second. But I want to sum up. So let me get a big sigma in here. Okay, there's my big sigma. So what I'm saying here is I'm going to sum up over all I this derivative here. So it's actually a bunch of chain rules summed together, because I have this path here, but I also have this path, that path, that path. So whatever the derivative was with respect to the ith component of AI, I multiply that by the weight from j to I. And I vary I and I sum them all together. So let me put this in a nice little parentheses here. So I'll get my parentheses going. I'll put the parentheses on the left here. And I'll put it on the right to close it out. And I'm actually almost finished with this. So this is part of it. And then this here, this is the derivative of hk with respect to ak. So that is the application of the nonlinear function, element-wise, to the elements of ak. So remember, we do the linear part, and then we put it through something like a leaky ReLU or sigmoid, just logistic function, whatever. And that is how we transform AK to HK. But this is done element-wise. So what it means is that the derivative of HK at index j only depends on the derivative at AK at index j. All right, now in practice, so this is actually the expression. This is the correct expression for the multi-layer perceptron case for updating, for computing the derivative of L with respect to AK at each component. But in practice, we're not going to actually write it out like a sum like this. You could. I mean, this is how it works. You could just make a loop to loop through each row at this column. But there's a more convenient way to write this actually as a matrix multiplication. So we have this matrix, capital W k plus 1. And so let me move this down out of the way so I can show the simplification. So we have this matrix wk plus 1, and what we're doing here is we're taking a dot product of the entire row, or sorry, the entire jth column of this matrix. So we're varying I, keeping j fixed. So that's going down the jth column. We're taking the dot product of the jth column with the entire vector dl dA k plus 1. So just as a sanity check, the jth column has m elements. The jth column of wk plus 1 has m elements, and so does the derivative with respect to ak plus 1. So that works out dimension-wise. The way to write this is actually, we actually need now the columns to be along the rows for this to work out with matrix multiplication. We're trying to, normally when we do matrix multiplication, we take the dot product of each row of what's on the left with each column with what's on the right. This is a column on the right, dl dA k plus 1. So now I'm not going to index it with I, but I'll leave it as is, remembering that this is actually a vector. I have the column on the right, but I intend to take the dot product with columns of wkt plus 1. Or sorry, wk plus 1. So I actually have to take what's known as the transpose. So I'm going to switch the rows for the columns here. And then I have what I'm looking for. So this matrix multiplication here of wk plus 1 transpose on the left, so switching the rows for the columns, with that derivative vector that I've remembered with respect to a plus 1, that gives us this entire thing in the parentheses. And then what I'm going to do is something called a Hadamard product. It's just the element-wise multiplication. So it's denoted by this weird symbol here. But so this here is a matrix. I'll be explicit about this. So this over here is a matrix multiplication. That's what's this part. And then this here is what's known as a Hadamard product, which is an element-wise multiplication. Okay. So we're multiplying this whole thing, actually this whole thing over here on the left, once we've evaluated that. So that's first in the order of operations. I should keep those parentheses here probably, just to emphasize that. So we do this matrix multiplication first, and then we can do the element-wise multiplication of the result of that with each component of the derivative of the nonlinear function with respect to ak. All right, cool. So this is great. We're making a lot of progress here. We have most of what we need actually. So this is the derivative of L with respect to AK. This is the entirety of it. It's actually a whole. It's a column matrix. It's an entire vector. So it's this expression here. That's how we get it from the derivative with respect to AK plus 1. All we need to know is the weights matrix k plus 1 and the derivative of the output of the nonlinear function that's applied at this layer that gets us from AK to HK. All right, so we're almost there, but we have to now deal with this down here. So this is kind of interesting. We're going to have certainly some similar stuff. So I might as well go ahead and copy this in the place of what we had before. So now we're looking for the derivative of L with respect to the... We're looking for the derivative of L with respect to the weights at this layer. So we've got the derivative with respect to the biases, and also that's something we're going to remember for the next time. But now we need the derivative of the loss function with respect to the weights. So there's one extra term here. That's hk minus 1. So this is something that I would have remembered from the forward pass. So actually, it gets a little bit confusing with the indices because I always want to refer to a row index of a matrix as I and a column index as j. So I'm going to pick a different j and a different I over here. So let me pick, maybe I'll say this j, and maybe this I. So now I'm looking what kind of one layer back. So I've kind of shifted my perspective on what is the output and what's the input. So I'm going to refer to the input always as j and the output as I. And so I look at this equation here, and I notice that, okay, what I'm actually looking for on the left-hand side here, my WK has p row, or sorry, n rows and p columns. This is actually an entire matrix. So let me index it with 2 coordinates now. So actually, I'm going to have an entire matrix of derivatives here. This expression that I was just working on actually now gives me the ith component of this vector. So remember, now I'm indexing it with I, okay, because I'm looking one back. This gives me the ith component of this vector, which is the derivative with respect to ak. So I have the ith component of that. And actually that now only because, okay, so I have, let me back this up here, because now if I'm looking at the influence of the jth input to my layer here on the ith output, then that's going to be described by the weights matrix K at index ij. In this case, that's actually the only weight that influences the derivative of row I and column j. So the derivative of the loss function with respect to row I and column j. That's the only weight that's involved here. So actually, we're holding all the other weights fixed. So unlike before, where we actually had to worry about all these weights coming out of j into I, for this derivative, we're actually only looking at one weight at a time. And so we don't need a sum anymore. We're just going to take the ith component of this thing that we already worked on and multiply it by the jth component of the input hk minus 1 into this layer. Okay? So just checking this is all consistent with the indices that I chose up here. And once again, there is a more convenient way to write this as a matrix product. hk plus 1 is a column vector. This is also a column vector. If I want to write the entire matrix of derivatives here, of the loss function with respect to wk, as just a matrix multiplication, what I can do, so I'll take out the indices here to emphasize that I'm actually computing the entire matrix now. What I can do is take this column vector, keep it on the left, but then multiply on the right by the transpose. So we're going to turn this column vector into a row vector. We're going to multiply by the transpose of hk minus 1. So we're turning hk minus 1 into a row vector now. Let me get all my parentheses set up here so it's super clear, the order of operations, what that's supposed to be. So actually, I mean, this is something that you can reuse, right? I mean, this is something would have already computed up here. I could just plot that down in here, and then just do this matrix multiplication by hk minus 1 transpose. So to check to make sure the dimensions work out, I should have n rows and p columns in my matrix of derivatives here. So let's check. This matrix here is a column matrix. As I was looking before, this AK, the derivatives with respect to AK, is supposed to have n rows and m columns. So that would be n rows and 1 column. So it's a column matrix with n rows. And this here was a p by 1 matrix. So it's a column matrix with p rows. When I take the transpose, that turns into a 1 by p matrix. And so you see when I multiply these two together, I then get an n by p matrix, which is perfect. So good. So the derivative of the loss function with respect to wk has n times p components, which matches up exactly with the dimensions of wk. That's perfect. Okay, so just to see how far we've come here, if we go back to the lazy calc version and see how we were doing the derivatives, we did indeed make a matrix of derivatives that had the same shape as our weights matrix. But to fill it in, we actually had to do a separate computation, a separate full forward path on the entire network, just to fill in a single row and a single column. But now we can fill in all the rows and all the columns with just this matrix multiplication. And this is actually quite cheap. Once we've computed this, it's just what's called an outer product here. It's just a column matrix times a row matrix. So these are all the rules for backpropagation in a multi-layer perceptron. It's really not that bad, actually. Once you finish reasoning through and getting all the shapes right, that's a bit of a pain. But once you get that done, it's just these equations here. And it's really not that much worse than what we had down here. Okay, so instead of just these scalar multiplications, they turn into various matrix multiplications. And that's what I'm going to have you do in the next homework. So I've written this up in some pseudocode that you can look at. And you just follow this. But if you want to go back, I'm all about doing things from first principles, so it's very important for me to actually show you how this all worked. But you will get some hands-on experience actually implementing this in the homework. Good. So I hope that helps you, and I hope that makes you feel satisfied. I had a difficult time finding this. I really ended up having to do it by myself and work it out by hand to really get it. So I hope this ends up being a valuable resource for people. Doing matrix derivatives is a little bit complicated, especially if you're not used to matrices. And I just kind of introduced them in this course. Linear algebra is not a prerequisite. So I hope this helps people. All right.